Class 6 Chapter 9 Electricity in Circuits. Introduction to Electricity. Definition. Electricity is a form of energy resulting from the presence and flow of electric charge. It is a fundamental aspect of modern life and is used to power various devices, machines, and systems that we rely on daily. Discovery. The understanding and practical application of electricity have evolved over centuries. The ancient Greeks were aware of a substance called amber that, when rubbed, could attract lightweight objects. However, it was not until the 17th and 18th centuries that significant advancements were made in the field. Benjamin Franklin's experiments with lightning and his famous kite experiment led to the concept of electric charge and the invention of the lightning rod. Nature of electricity. Electricity is based on the movement of tiny particles called electrons, which carry a negative charge. These electrons flow through conductors, such as wires, and create an electric current. The behavior of electricity is governed by fundamental principles like voltage, current, resistance, and power. Generation. Electricity is primarily generated through various methods, including fossil fuels, coal, oil, and natural gas, nuclear power, renewable energy sources, solar, wind, hydroelectric, geothermal, and more recently, advancements in technologies such as tidal and wave power. These methods involve converting other forms of energy into electrical energy through generators or power plants. Transmission and distribution. Once generated, electricity needs to be transmitted and distributed efficiently to where it is needed. High-voltage power lines are used to transmit electricity over long distances, and transformers are used to step up or step down the voltage for efficient transmission and distribution. Local distribution networks then deliver electricity to homes, businesses, and industries through lower voltage lines. Applications. Electricity has a wide range of applications in various aspects of modern life. It powers our homes, lighting systems, appliances, and electronic devices. It fuels industries, enabling manufacturing processes, transportation systems, and communication networks. Furthermore, electricity is crucial in healthcare, powering medical equipment, diagnostic tools, and life-saving devices. Importance and impact. The availability and reliability of electricity have a profound impact on society and the economy. It has transformed industries, revolutionized communication, improved living standards, and enabled technological advancements. Electricity is closely linked to economic growth, and access to reliable electricity is considered a vital factor for development. Electric cell. An electric cell, also known as a voltaic cell, is a device that converts chemical energy into electrical energy. It is a simple and portable source of electric power commonly used in various applications. Here's an introduction to electric cells. Structure. An electric cell typically consists of two electrodes, an electrolyte, and a casing. The two electrodes are made of different materials, often metals or metal compounds, and are immersed in the electrolyte solution. The electrodes are connected externally through a circuit, allowing the flow of electric current. Chemical reactions. The functioning of an electric cell is based on chemical reactions that occur at the electrodes. One electrode, called the cathode, undergoes reduction, where it gains electrons. The other electrode, known as the anode, undergoes oxidation, losing electrons. These electron transfers create an electric potential difference between the electrodes. Electron flow. The electric potential difference generated by the chemical reactions causes electrons to flow from the anode to the cathode through the external circuit. This flow of electrons constitutes an electric current that can be used to power various devices or perform work. Electrolyte. The electrolyte, a solution or paste, plays a crucial role in facilitating the movement of ions within the cell. It allows the transfer of charged particles between the electrodes, maintaining electrical neutrality and ensuring the continuity of the chemical reactions. Types of electric cells. There are various types of electric cells, each utilizing different electrode materials and electrolytes. Common examples include the zinc-carbon cell, alkaline cell, nickel-cadmium cell, and lithium-ion cell. These cells differ in terms of their voltage output, energy density, lifespan, and suitability for specific applications. Applications. Electric cells are used in a wide range of applications, including portable electronic devices like flashlights, remote controls, and wristwatches. They are also employed in larger-scale applications such as powering electric vehicles, providing backup power in uninterruptible power supply (UPS) systems, and serving as the primary power source for satellites and spacecraft. Rechargeable cells. Some electric cells, known as rechargeable cells or secondary cells, can be recharged by reversing the chemical reactions that occur during discharge. These cells are designed to be used multiple times, making them more cost-effective and environmentally friendly compared to single-use cells. Filament. A filament refers to a thin, elongated wire or thread, typically made of a material that can conduct electricity and generate light when heated. Filaments have various applications, particularly in the context of lighting. Here's an introduction to filaments. Light bulb filaments. The most well-known use of filaments is in incandescent light bulbs. These bulbs consist of a glass envelope filled with an inert gas and a filament made of a material such as tungsten. When an electric current passes through the filament, it heats up to a high temperature, emitting visible light as a result of incandescence. Incandescent lighting. Incandescent bulbs have been widely used for general lighting purposes. The filament's resistance to the electric current causes it to heat up and glow, producing a warm, yellowish light. However, incandescent bulbs are not as energy efficient as other lighting technologies and have largely been phased out in favor of more energy efficient alternatives. Tungsten filaments. Tungsten is a commonly used material for light bulb filaments due to its high melting point and resistance to heat. Tungsten filaments can withstand the high temperatures required for incandescent lighting, allowing them to emit a steady and long-lasting light. Halogen lamps. Halogen lamps are a type of incandescent lighting that uses a tungsten filament enclosed in a halogen gas-filled envelope. The halogen gas combines with the evaporated tungsten atoms, preventing the formation of a blackening layer on the bulb's anterior surface. This process enhances the lifespan and efficiency of the filament, making halogen lamps more durable and brighter than traditional incandescent bulbs. Filament in 3D printing. In the realm of additive manufacturing, or 3D printing, the term filament refers to the material used to create physical objects. These filaments are typically thermoplastic polymers, such as PLA, polylactic acid, or ABS, acrylonitrile butadiene styrene. The filament is fed into a heated extruder, which melts the plastic and deposits it layer by layer to build the desired object. Carbon filaments. Before tungsten, carbon filaments were commonly used in early incandescent bulbs. Carbon filaments were made by carbonizing organic materials, such as bamboo or cotton thread, which were then enclosed in a vacuum or inert gas-filled bulb. While carbon filaments are less efficient than tungsten filaments, they were crucial in the development of electric lighting technology. Filaments in vacuum tubes. Vacuum tubes, which were widely used in early electronics, also employed filaments. These filaments, often made of tungsten or other metals, functioned as a heated cathode. When the filament was heated, it emitted electrons that played a vital role in the operation of the vacuum tube. A bulb connected to an electric cell. When a bulb is connected to an electric cell, it forms a simple electric circuit. The electric cell acts as the power source, providing the necessary voltage to drive the flow of electric current through the circuit. The bulb, also known as an electric light bulb or lamp, consists of a filament enclosed in a glass envelope. The filament inside the bulb is typically made of tungsten, which has a high melting point and can withstand the heat generated when electricity passes through it. When the circuit is complete and the electric current flows through the filament, it heats up and emits light due to incandescence. The brightness of the bulb is determined by the amount of current passing through the filament. The glass envelope of the bulb is designed to contain the filament and protect it from the surrounding environment. The electric cell's positive terminal is connected to one end of the bulb, and the negative terminal is connected to the other end, completing the circuit. As long as the circuit remains closed and the electric cell has sufficient power, the bulb will continue to emit light. If the circuit is opened and the electric cell loses its charge, the flow of current stops, and the bulb no longer emits light. An electric circuit. An electric circuit is a closed loop or pathway through which electric current can flow. It consists of various components that work together to allow the flow of electrons from a power source to perform specific tasks. Here's an introduction to electric circuits. Components. An electric circuit typically includes several components. Power source provides the electrical energy to the circuit, such as a battery or generator. Conductors, materials, usually wires, that allow the flow of electrons. Load, the device or component in the circuit that consumes electrical energy to perform a specific function, such as a light bulb or motor. Switch, a device that can open or close the circuit, controlling the flow of current. Resistors, components that restrict the flow of current in a circuit, often used to control the amount of current reaching a load. Pathway, the components in an electric circuit are connected together in a specific arrangement, forming a pathway for the flow of electrons. The path starts from the positive terminal of the power source, travels through the circuit's components, and returns to the negative terminal of the power source. Current flow. Electric current refers to the flow of electric charge, usually carried by electrons. In a closed circuit, electrons flow from the negative terminal of the power source to the positive terminal, propelled by the electric field created by the power source. The current flows continuously as long as the circuit remains closed. Series and parallel circuits. Electric circuits can be arranged in series or parallel configurations. Series circuit. In a series circuit, the components are connected one after another, forming a single path for the current. The current is the same through each component, but the voltage is divided across the components. Parallel circuit. In a parallel circuit, the components are connected across multiple branches, providing multiple paths for the current. The voltage is the same across each component, but the current is divided among the branches. Ohm's law. Ohm's law, named after the German physicist Georg Simon Ohm, describes the relationship between voltage, V, current, I, and resistance, R, in an electric circuit. It states that the current flowing through a conductor is directly proportional to the voltage applied across it and inversely proportional to the resistance of the conductor. Mathematically, Ohm's law is expressed as V equal to I multiply R. Circuit analysis. The behavior of electric circuits can be analyzed using various principles and techniques, such as Kirchhoff's laws and circuit diagrams. These tools help understand the distribution of voltage and current in complex circuits and facilitate the design and troubleshooting of electrical systems. Applications. Electric circuits are essential in numerous applications, from powering household devices to complex electronic systems. They are used in lighting, heating, communication systems, computers, transportation, and a wide range of electronic devices and appliances. Electric switch. An electric switch is a device that controls the flow of electric current in an electrical circuit. It is used to open or close a circuit, allowing or preventing the passage of electric current to connected devices or components. The switch consists of a contact mechanism that can be manually operated or triggered by other means, such as a sensor or timer. When the switch is in the on position, it closes the circuit, allowing the electric current to flow through the circuit and power the connected devices. When the switch is in the off position, it opens the circuit, interrupting the flow of electric current and cutting off power to the connected devices. Electric switches come in various forms, including toggle switches, push-button switches, rocker switches, rotary switches, and many more, each designed for different applications and user preferences. The position of the switch, on or off, is typically indicated by visible markings or an indicator light. Switches can be installed in electrical panels, control panels, walls, or embedded within devices or appliances. Electric switches are widely used in homes, buildings, industrial settings, and electronic devices to control lighting, appliances, machinery, and various electrical systems. They provide a convenient and safe means to control the flow of electricity, allowing users to turn devices on or off as needed and ensuring electrical safety by cutting off power when necessary. Electric conductors and insulators. Electric conductors. Definition: electric conductors are materials that allow the easy flow of electric charge or electric current through them. They have a high density of free electrons that are loosely bound and can move freely within the material. Conductivity. Conductors have high electrical conductivity, meaning they offer low resistance to the flow of electric current. This property allows them to efficiently transmit electrical energy. Examples. Common examples of electric conductors include metals such as copper, aluminum, silver, and gold. These materials are widely used in electrical wiring, power transmission lines, and various electronic components. Free electrons. In conductors, the atoms have loosely bound outer electrons that are not strongly attached to their nuclei. When an electric potential difference is applied across the conductor, these free electrons move in response to the electric field, creating an electric current. Heat and electricity. Conductors also exhibit good thermal conductivity, meaning they can efficiently transfer heat. This property is useful in applications where heat dissipation is necessary, such as in heat sinks or electrical connections. Electric insulators. Definition: electric insulators, also known as non-conductors or dielectrics, are materials that impede the flow of electric charge. They have tightly bound electrons and do not allow the movement of electric current. Insulating properties. Insulators have high electrical resistance, which restricts the flow of electric current through them. They act as barriers to prevent electrical energy from escaping or unwanted electrical interactions from occurring. Examples of electric insulators include materials like rubber, plastic, glass, ceramic, and wood. These materials are commonly used in electrical insulation, such as insulating coatings, cables, and insulators for electrical equipment. Electron bonding. Insulators have their electrons tightly bound to their respective atoms, making it difficult for electric charges to move freely within the material. The valence electrons remain localized around the atoms, preventing the flow of electric current. Safety and protection. Insulators play a critical role in electrical safety by preventing accidental electric shocks. They also provide electrical insulation, reducing the risk of electrical short circuits and protecting against damage or interference from external electrical fields. Dielectric materials. Insulators are also used as dielectric materials in capacitors, where they store electrical energy in an electric field. Dielectrics exhibit polarization when subjected to an electric field. Storing and releasing energy is needed.